let's talk about the future. And not the far-off flying cars future, but what's happening right around the corner. We're looking at 2026, which is shaping up to be a huge year for AI. Because this is when AI is really set to break out of the digital world and get physical. We're talking about moving from just code in the cloud to actual robots that walk, work, and interact right here with us. So let's dive into what that massive shift is really going to look like. So to really get this, we have to start with the one problem that has obsessed robotics for decades. Ty Brady from Amazon Robotics puts it perfectly. He calls it the manipulation problem. You know, something as simple as picking up a glass of water is, for a machine, an unbelievably complex task. It's been the holy grail of this entire field, and we are finally starting to see some real cracks in the armor. And that really is the central theme for 2026. AI is getting a body. It's moving out of the cloud and into the messy, unpredictable physical world. And this isn't just about running better software. It's about forcing intelligence to learn from direct physical interaction with reality itself, not just from clean, static data sets on a server somewhere. So what is the big difference here? Well, this table just lays it out beautifully. Your traditional AI, it lives in a digital world. It processes text, images, code. But embodied AI, it has to operate in our chaotic, unstructured, three-dimensional space. And its main challenge isn't just spitting out the right answer. No, it's challenged to perform a physical action in real time and do it safely and efficiently. It's a whole different ballgame. So here's the game plan for this explainer. We're going to look at the new kind of brain these robots will have, the hardware that brain runs on, the absolute nightmare of deploying them in the real world, the risks that come with that, and then a pretty radical new idea for making them safe. Okay, so let's get into the solution that pretty much the entire field is betting on right now. It's all about giving robots a totally new kind of brain, one that can actually see the world, understand what we're saying in plain language, and then translate all of that directly into physical action. And these are called Vision Language Action Models, or VLAs for short. They are absolutely the dominant paradigm right now, and here's why. They inherit this vast, almost common-sense understanding of the world, because they've been trained on just enormous amounts of internet data. So when you tell a VLA to pick up the red cup, it already has a concept of cup, it knows what red looks like, and it can connect those ideas to the motor commands to actually do it. It's a total game changer for getting robots to do more than just one repetitive task. Which brings us to our first huge prediction for 2026. We are about to seriously test the scaling laws for robotics. Right now, the fanciest VLAs have around, say, 7 billion parameters. But by the end of 2026, we're expecting to see models with over 100 billion parameters. That's not just a step up, that's a whole new staircase. And the hope is that this massive scale will unlock abilities in physical reasoning that we just haven't seen before. But listen, it's not just about making them bigger, it's also about making them smarter, with new architectures for reasoning. You see systems like Google's Gemini Robotics starting to implement a thinking before acting process. So they can take a complex command, something like sort the laundry, and before a single motor moves, they internally break that big problem down into a logical sequence of smaller, doable steps. Okay, but here's the massive catch. You've got this giant new brain. How in the world do you actually run it on a physical robot that has to, carry its own battery? This leads us to the next critical problem everyone is racing to solve, the hardware gap between the cloud and the edge. And what's so fascinating here is just the sheer scale of this challenge. I mean, look at these numbers. The memory bandwidth on a top-of-the-line data center GPU is over 3,000 gigabytes per second. On the best chips we can put in a robot today, it's about 60. That's a 50 times gap. Let's be real, you simply cannot strap a data center to a robot's chest. And this hardware problem isn't just about raw computing power. It's also about giving robots better senses. This chart is so telling. It shows what happens when you add tactile feedback, a sense of touch, to these VLAs. For really precise, contact-heavy tasks like plugging in a charger or inserting a peg into a hole, adding touch can boost the success rate by over 15%. That's huge. It's the kind of thing vision alone just struggles with. So, okay, let's just imagine for a second that we solve all that. We get bigger brains, we get better senses. Well, what we're discovering is that in the real world, this success actually creates a whole new set of even harder problems that we're only just now starting to face. And this, right here, this is the dirty little secret behind most of those cool VLA demos you see online. It's the problem of long horizon tasks. Let's say your robot is amazing, with a 95% success rate on any single step. That sounds great, right? But the brutal math of compound error means that the probability of successfully finishing a 10-step job plummets to less than 60%. And that is why most demos are just single, simple, repetitive actions. And this brings us to the commercial reality check for 2026. Despite all the hype and all the cool videos of humanoid robots, our prediction is that the simpler, more reliable mobile robots, the kind you see zipping around warehouses, they're going to continue to dominate actual commercial deployments by a ratio of at least 10-to-1. They're just more stable, and they're better at solving those high-volume, low-variety tasks that businesses actually need done. But the humanoids are coming. And as these much more advanced, much more complex robots start operating near people, the stakes just get exponentially higher. A mistake is no longer a little digital error message. It's a physical event with very real physical consequences. And you know what? The incidents are already piling up. Throughout 2025, we saw this string of very public malfunctions, from a robot nearly headbutting a person, to another one flailing uncontrollably near factory workers, to one just collapsing on stage. And these events are putting robot safety under intense public, and you can bet soon legal scrutiny. So here's the bottom line, and robotics pioneer Rodney Brooks puts it pretty bluntly. Bipedal robots are just inherently dangerous when they lose their balance. And with companies pushing so hard for real-world deployment, a major safety incident feels less like a possibility and more like an inevitability. And that is what's going to trigger some very serious regulatory attention by 2026. So this growing risk is forcing the entire field to think beyond just simple rules like don't harm humans. And this leads us to a new conceptual framework that looks at safety not as a feature you add on top, but as a core principle of the architecture itself. It's called the MONADA AXIO protocol, and it's described, pretty poetically, as a form of cognitive metallurgy. The idea here is to completely shift gears. Instead of just making AI bigger and more capable, the focus is on forging a logically sound, internally consistent system from the ground up. Kind of like how a metallurgist forges steel to hammer out all the impurities and create something strong. And this slide really nails the difference in philosophies. The standard approach today is basically to police the robot's behavior from the outside, right? We use benchmarks and high-level rules, these robot constitutions, to try and guide it. The MONADA AXIO approach is totally different. It tries to build logical integrity right into the core of the system to prevent a kind of internal cognitive collapse before it can even result in a dangerous action. So how does it actually do this? Well, it uses formal logic to hunt down and fix internal contradictions, what the protocol actually calls logical crimes. The whole point is to prevent a kind of systemic schizophrenia, where different parts of the model are essentially fighting each other. It even uses a special mathematical technique to get rid of the performance hits that safety training often causes. The goal isn't just to pass a test, but to be provably stable.